Hey, hi everyone, this is Vivek and welcome to this third week of Atcoder Weekly. Today we're going to talk about this problem 2 exams from Atcoder Beginner Contest 238. And this is a really cool problem. This is going to be a video in which I'm going to try and explain the intuition behind dynamic programming through this particular problem and how to create solutions for any general problem for that sake. From this video onwards, there is a quick announcement that we're going to have a target for the number of comments, because as per the format is for every video of this weekly series, I kind of ask you guys to comment down below what is the learning that is there. So since there needs to be a motivation for the people who are watching out these contents, so there's going to be this one thing that the next video comes up when at least there is 100 comment onto this particular video, because at least 1000 people watch these things and I feel there is a good amount of learning on these. But if you're not commenting enough, I think those things are going to go to almost like waste, right? So we're gonna keep a target of 100 comments. करा दो यार, क्या है इसमें, like एक comment करना आपको क्या सीखा इस वीडियो में, ठीक है, कुछ भी जो आपने सीखा, right? Okay, cool. Next, move forward to this particular problem where we have 2 exams where we talk about whatever this particular setup is, and we're going to talk about the different reading, observation and formulation phase as we do for every other video, right? So let's talk about this problem now. In this kingdom of Takeshi's, there is examination. So there is given that the citizen I has PIth rank in the first test and QIth rank in the second test. So there are 2 tests that is happening, and it's like there is no clashes. So everything is a permutation of 1 to n. Now you have to select kx citizens for the national team. Okay, so we have to choose k items out of this n people, and what we need to ensure is that there should be no pair x comma y such that citizen x is selected, y is not selected, and px is also bigger than y and qx is also bigger than y, which means like both the metrics, both the ranks for the person selected is worse than a person not selected, right? I mean, it's kind of saying that, okay, a person was not selected and a person was selected, x was selected and y was not selected, and x performed worse in both the tests. So that makes sense, right? So we need to find a number of ways to find such a team that satisfies the given condition modulo some prime number, right? That's the question. And the constraints for this problem is n up to 300 and k is obviously up to n, and then p and q's are permutation of 1 to n, right? And there are some sample inputs given to us, right? So if we think about this particular problem, the first thing that should click in your mind instantly after looking at this problem is that n is up to 300, which means these kind of constraints generally hint towards dynamic programming solutions, and that's why how we can kind of go into the route of dynamic programming. Now, if you try to analyze the problem very carefully, what is it exactly trying to say? That we have n items, we have to choose k items out of that such that some condition hold true, right? That's the whole thing. So n items, out of that you have to choose k items certain given some condition is true, right? So how do we model this thing, this constraint that is given to us out of all selection, right? The first thing that you should observe in these kind of problems is there is n people which is unordered, right? I mean, we have to just select k citizens. It's not like the ordering of those k citizens matter, right? So there are 2 dependencies over here, px greater than py and qx greater than qy, and handling 2 dependencies is quite difficult. Like you have to go into two-dimensional zone, right? So one thing that you can try and do to help us is maybe sort the people by the score in the first test, by the rank in the first test, and then try to balance out the second one, right? So let's try and see what is happening over here. So let's take the sample input itself. Let's have a look at what the sample input talks about. So there is 2431, 2143. 2431, 2143, right? So let's say this is the P test, Q test, right? So now whenever we are kind of given these 2 ranks for the people for the n people, we have to first realize that, okay, for any 2 person, if px is less than py and qx is less than qy, then there is a problem in these 2 person, right? So this one dependency over here among all the elements can be resolved off if we just try and select the elements in the sorted order of the P, right? I mean, whatever we choose, we're gonna choose like in the increasing order. So let's say we rearrange these items. So 1, 3 starts first, then 2, 2, then let's say 3, 4, and then 4, 1, right? So this is there. Now, if we choose any set over here, right? Any set over here. So for every item, like the previous, it's not going to have any conflict with any of the previous items x, right? Because the x's are already increasing. So if we choose this thing in the set, it will have a bigger px. So in that case, it has a smaller qi. at least, so that it can be selected, right? So that is there. So first thing that comes into mind is sorting these things by one of their parameters so that one constraint gets removed, the other still remains, right? Qx is less than Qy. Okay. So now we have this problem that this is kind of sorted on one of the ends, right? And the other thing is coming up as per the sorting order of the first one. Since they are permutations, there is going to be no conflict altogether. And we need to find some sort of way to select elements such that, like if we select this first element over here, so you have selected 1, 3, right? Now note that you cannot really select, and let's say you don't select the second one, then you cannot really select this, let's say 3, 4. Can we select this 3, 4? So 3, 4 performs worse than this one, and it also performs worse on this one, right? So if you did not select this, you cannot really select this, right? So this is what we have to kind of keep track of, that what we can select and what we cannot. And as you can see that since the first one is increasing, the only thing that matters is what is the condition for the second one so that we can select it or not, right? So this now moves into the domain of dynamic programming and how do we do these kind of things. Now let's talk about a general framework for these kind of problems. Whenever you have a dynamic programming where you have to choose some subset out of n sets, right? It's a form 1 DP. I'm not going to explain what form 1 is right now, but essentially what we try to write is DP of particular I, which means, or you can call it as level, okay? Which essentially says that if you are left with level till n item, right? You start with 1 till n, right? All of these items are present. If you have decided the things for 1 till level -1, okay, and you are currently at the current level and you have to decide whether to take this or not, right? What is that corresponding values are going to be is what we try to keep in this level, okay? So which item are we currently iterating on? Next thing that we try to keep in this case is we have this limited quantity of positions in the team, right? Which is k in this case. So we have to keep a count. So this is something that is very general in DP. You have to understand what is the things that are going to be, how are different kind of constraints, like total count of items less than k, sum of items less than p, and so on. Knapsack is essentially the second kind, right? So how are these kind of constraints modeled in the states of dynamic programming? This is what comes with practice, okay? These are things that I've talked about in one of the videos. You can check that out on dynamic programming on my channel. If you go to that, I will also link it up in the I button. And for that particular case, we have to keep track of number of items taken, right? Next thing that we have to talk about is whether to kind of take, when we are trying to take a particular item, what matters, right? So any item that we have not taken before is potentially going to like create a conflict with this particular item, provided that this is smaller than the next item that we are currently considering. So let's say we are considering this item, right? 4 over here. So if there is any item whose Q value is lesser than 4, right? That has not been selected, that is going to be a problem, right? And out of, let's say there is 3, 4, right? There is, let's say 2, 2, 1, 1, let's say 1, 9, something like 0, I'm just arbitrarily creating ranks right now, but I hope you got the point. Let's say 3. So for 4, these two can create a problem, right? But let's say if this was not taken and both of these were not taken, right? In that case, the smallest of the two decides what can be taken or not, right? Because 2 is the smallest one that is not taken, and anything above 2 is going to be problem because P is bigger than that. P is already in increasing order, and then even Q will be increasing in that case. So that is going to be the conflict. So the main key constraint that you have to keep, main state variable that you have to keep to check this constraint, right, is minimum Q not taken. And believe me, this is all about DP. You have to understand how to model different constraints in question into the different state parameters that are there. This is what practice essentially builds in DP. If you are doing this well, you are actually going to be performing really well in DP problems, right? How to model different constraints into states. Optimization and things comes later on, but this is what essentially happens, right? So this is the whole thing that we kind of think of, right? And what should this DP return, right? So what is the question asked in the problem is what the DP should return. Find the number of subsequence of size n in that sense, right? So let's say find the number of subsets possible, and there are these parameters, right, where number one, the items from level till n are yet to be decided. You have already decided the items, like the choice of taking and not taking for the items in 1 to level -1. The number of items and taken is kind of present over here, and not taken's min is present over here. So with these two extra information with you in the states, what is the number of subsets that you can create is what you've returned from the DP. So this is all about formulating. Let's try to formalize this particular thing in terms of like building the state and transition. But this is essentially the first step that goes into any DP solving. That how do you model this problem? How do you model the constraints into states of the DP? Right? Let's move on to how do we like kind of formalize this. So there are like, let's say person 1, person 2, person 3, and so on, person n, and their p values are sorted. Okay. I'm assuming that p's are already sorted by that, for that matter. And then we're gonna say that dp of a particular level I, you are currently considering the element at I, right? And these are items that are left to be decided whether to take it or not. These had already been decided, and the number of items that has been taken till now is, let's say, j. Okay, this is taken. Okay, number of items that are already taken among these, right? And the minimum not taken, minimum not taken is going to be over here. Is, let's keep it as m, minimum not taken. So initially we have no items not taken, so it can be kept as something like an infinity, right? So from this particular state we have two choices, right? This is essentially a standard style, okay, which is of form 1, where we essentially decide that whether to take this or not, right? The decision is essentially to take this or not. So this is the state based on what are the constraints that we have to model. Now we have to design the transition. How to design the transition? It's essentially take or not take, right? That's the action, right? Now when you have to take, let's say this is the taking action. So if you try to take it, when is this possible? This is conditioned on if q3 is strictly less than m, because anyways all the numbers of q's are distinct. If it's strictly less than n, then only we can take this particular item, right? Because, or else if it's bigger, then like p2 is less than p3, q2 is less than q3, and then we have not taken some, let's say, previous item, right? So this is the whole condition for this branch to be active. And if it is active, then what we can do is we can actually go ahead and take this item and go to I plus 1, like try to decide the number of subsets that we can generate using this configuration. And we have taken one more item now, and the minimum remains the same because we are taking this, so minimum doesn't really change, right? These are the number of ways by which you can create a subsequence by taking it. So the whole decision till now is up to this, right? The other way to do it is not take it. In that case, we will go to dp of I plus 1, decide the next items. We don't take this, so number of items taken doesn't change. And then we have the minimum not taken as minimum of the previous minimum and the q of the current I, right? That's the two thing, right? This is how you write the transition based on the action. So it's essentially saying, what are the number of subsets that are there that you can generate from the rest of the items, such that these are the things that you have done from the first items, and this is what you have reached as of now. And this is going to return the number of ways. This is going to return the number of ways. And since this is a counting problem, in any counting problem, you essentially add the things, like you add the things. That is how the combination happens. So this is the condition for this. This is going to be there in the if condition. Like if q3 is less than m, then you kind of add this into the answer, or else you add this into the answer. There's always a choice to not take anything, right? And essentially you just add all of these things together and you get the final answer. Now there are a few more considerations to do into this whole thing. What is the base case going to be look like? And base case is when you reach the final end, that you are reaching the whole n position over here. From you start from 0 or let's say 1 and you reach n plus 1. That's the position where you decide, okay, you don't have any more choices. So if the number of items taken is equal to k, if you want to fill it all together, and based on that you can, and anyways, like you are not taking any faulty transaction. So everything that generates at that point is correct. So anything that you reach, so we're gonna call dp of 0, or let's say 1 in this case, since we are writing it 1 indexed, but in coding you're gonna write it as 0 indexed. We're gonna call this number of taken right now is 0 before 1. So you start over here, you're starting at this index 1, you have not taken any item over here, the minimum till now is infinity. So we can keep something like n, maybe that is not going to be a problem, because n is going to work like infinity over here, right? Because we're checking strictly less than. So this is what we call, and essentially this is going to go into generating the number of ways, number of solutions that are there. And the way we're going to mark the base case is when I is equal to n plus 1. That's the base case, because at that point in time there is no more choice, because at n you have the choice to take it or not take it, but at n plus 1 there is no more choice. So whatever you have generated, if j is equal to k, I mean don't even let j to be more than k at all places. Like I think the condition over here should be modified to, and there is a possibility to take more elements, right? So in this case you can take that element. And if j is equal to k, then you have a full team, right? If this is there, then return 1 or else return 0, right? That's the whole code, right? So this is going to be the whole like structuring up of the DP thought that you have to do for this problem, or for any problem in that matter, for that matter. And then you finally go about, okay, this is the call that I will do, this is the final like base case, and you're done with the whole problem. Now for this one problem, I'm going to show you how you can actually formulate the code and structurally write the code as well a bit, because I think I'm kind of covering this DP problem, DP style of writing for the first time on the channel. I mean, I've talked about it in one of the previous videos, do check it out. But still, if you still want to like check out how to write these things, convert this whole thought process into code, the way we do that is you first write, okay, you have a count. So we can write an integer. Obviously things are going to be done mod, so I'm not writing the modulo part into the code, but let's say you are returning something like a recurrence, okay, where integer the level is there, integer the number of taken items is there, and integer the minimum take that you have seen till now is there, right? And then what we're going to do is we're going to write the pruning conditions, not really required. I mean, we can do something like if j is greater than k, number of items is greater than k, then return 0, something like this can be done, right? So this is say pruning. Next, what we can do is if j is if I is equal to n plus 1, right? In that case, what we can do is if I can write it over here in this separate color. If k is equal to if j is equal to k, that we have taken the full team, then return 1, because note that the way we are going into the DP, we are never violating the condition that is given in the problem. So everything that generates at the base case is a valid solution. So return 1, right? Or else return 0. So this is the base case, right? Let's next. So over here, we're going to write a memo code, but that's not required for now. Let's write the transition. So DP, so we're going to write an answer for this variable, for this particular state. What is the answer? Answer is going to be equal to, if you don't take it, we're going to reach DP of I plus 1. And we are not taking it, so number of item does not change. And M is going to become min of the M comma Q of the current I, right? This is going to be the new value of this, right? And this is anyways possible. You can always not take items. And one more possibility is if, let's say, we have said that the Q of I is less than the current M, then we can take this item. So answer plus equals to DP of I plus 1, J plus 1, the same minimum, right? This is something that is possible. And this is what you store, return. We want to return answer, but now we add the memorization step over here, right? Now we add the memorization step. So we write DP of I think I should be writing recurrence over here, because the function name is recurrence. I mean, essentially it's just the DP, but it's just calling the function recurrence. It's going to return the value from the DP table itself, right? DP of I comma J comma M is equal to answer. And over here at memo, we're going to write, since it's counting, the like every value is going to be positive. So we can use if DP of I comma J comma M is not equal to -1, then return that saved value. right? So that's what we can do. And this is actually the whole code of this particular problem. I mean, this is going to be structurally the whole code. You have to add the modulos and everything in the code, but this is the structurally the whole thing. If you just write this recursive code and declare an integer dp over here, which is 300 in this case, and 301 actually, because we are reaching the last state, right? And we can kind of solve with this particular setup, right? So this is what is kind of required for this problem. Now, there are few optimizations on top of this. Let's say you have to optimize the first index, like since dp of I depends upon only I plus 1 over here, what we can do is we can save only the next level, and that can be done when you write it in an iterative fashion. So those are things I will leave on for you guys, but this is how the whole formulation process of dp works for this, right? So this is a really good problem to practice dp. Go ahead and solve this problem and solve it even in iterative manner if you want to get a good idea on how to convert these kind of codes into iterative. But this is how the logical process of building problems is there, right? Finally, once more, make sure that you comment what you learned in this particular problem. The whole formulation for this is gonna like one more thing that I should definitely cover is the time complexity. It's obviously going to be order n into k into n, because it's the number of states multiplied by the average number of transitions in general. So the number of transition is 2 and the number of states is n, k, n, right? So that's the total complexity, n square into k, right? So there are a lot of caveats into implementing these things maybe, but the whole thought process goes like this. So comment below what you learned on this, and we're gonna have this like rule that, okay, the next video is on this whole series, on Atcoder series, is gonna come out when we reach a threshold of, let's say, 100 comments. Okay, let's be a bit ambitious, but kara do yaar. I mean, there is a lot of channels which put out so much of generic stuff. ठीक है, बहुत लोग generic stuff डालते हैं, and like they do get a reach, and educational content कोई डाल रहा है तो उसमें तो कोई comment आएगा ही नहीं, है ना? But आप लोग करोगे जो लोग देख रहे हो अभी तक, I guess, I hope so, है ना? And I hope you guys support the content. We will keep creating more such things. This is on Tuesday, next Thursday, and like Friday, Saturday we're gonna have another lead code and codeforces ones. And if you want to look at more DP problems in those videos, do let me know in the comments, right? So that is also possible. Okay, so that's all for this one. I hope this made some thought process clear. See you in the next episode. Bye bye.